Good morning, students. Today we are going to discuss some uses of capacitors. Although each use will not be discussed in great detail, but some discussion will follow because that is important to understand that capacitor is a versatile device and the various uses that it is put to use has some relation to the topics you have discussed in various other topics as well, as you will see in these examples. The most important use of capacitor is its ability to use energy, store energy, and especially in those situations in which that energy is to be used in one go or in very short period of time. That means it is the energy which is delivered in short intervals in those situations where high power is required to start, for example, a reaction, a fusion reaction, or to start ignition of some process, to use energy as a flash, as in the flash cameras. So capacitors are very helpful in those situations in which the energy is first stored in large amount and then it is delivered in a very short period of time to any other circuit, to any other medium to start an ignition. So its ability to store energy. So capacitor as a device that stores energy, to deliver it in a short period of time, or simply to deliver that energy very quickly, instantaneously. So examples of this use, examples are flash cameras. They use that energy because that energy is first stored on a capacitor and then it is delivered very quickly in the form of a flash. We call it a discharge of energy. Another situation in which, as I have already said, it has a use in fusion reactors. In fusion reactors to start the process of fusion, because it requires huge amounts of energy to start a certain nuclear reaction, which is fusion in this case. So we can use very large sized capacitors because enormous amounts of energy is first stored. Sometimes it's not possible to store that energy by a single capacitor. In that case, we use a number of capacitors to store that much energy, and then that energy is quickly delivered. So that process of ignition is set in. So this is one of the uses of capacitor. Number two, capacitors are often used in conjunction with the other devices, notably inductors, but inductors are not discussed in your syllabus. So without naming that device, you can say that capacitors are used in tuning circuits. In tuning circuits, And in tuning circuits, capacitors are used as variable capacitors. They don't have a fixed value. You can change their capacitance. In old style TVs and radios, there was a knob, used to be a knob that was rotated to change the capacitance of the capacitor. And at a certain value of the capacitance, the tuning circuit tunes the radio to a particular frequency. That simply means it catches a certain channel. So a tuning circuit which tunes, used in a tuning circuit which tunes the radio or TV to a particular frequency, making use of resonance, because maximum energy is delivered to that circuit at that particular frequency. That means resonance has taken place, and we have already discussed this particular example of resonance as well. So tuning circuits, which is of course an electrical arrangement, an electrical equipment that is used for tuning the radio or TV or any other device to a particular frequency, making use of the already discussed process called resonance. So these are two uses of capacitors. Another one is, the third one, number 3. Capacitor is used in rectification that we'll study probably the next chapter. Rectification is the process of converting AC to DC. After the signal has been rectified to DC, there will still be a variation in it. In order to smooth, this is used to smooth out a rectified DC signal. After you have rectified AC to DC, there will still be a variation in it, there will still be a ripple in it. In order to smooth out that ripple, we use capacitors. Capacitor help us make it more like DC, and this is going to be a detailed discussion in the next chapter. So just remember, in the rectification we use capacitors in order to smooth out the signal. Number 4, capacitors are also used in order to measure time intervals, because they are devices which take specific, very precise time to charge and to discharge. That means if we know the values of the capacitance, the value of other components used in the circuit, we can very accurately measure the amount of time in which the capacitor has charged, and it takes the same time to discharge. So capacitors are very reliable devices to measure time intervals. So without going into larger detail in it, you can simply state this fact that capacitors can be used to measure time intervals. And if they ask how and why, you can simply add, because they take fixed or definite intervals of time to charge and to discharge, because they have fixed charging or discharging time, if the capacitance is unchanged, and if the resistance through which they discharge and charge is known. Another important use is known as coupling or decoupling, coupling of signals, which simply means that capacitors separate AC types of signals from DC. They allow AC to pass through devices, but they do not allow DC. So sometimes this is very, very important, because that is possible that AC passes through the device and serves a useful purpose, but when you allow DC to pass through the same device, it could be damaged. So in that case, coupling of signals is important. You separate one signal from the other, you allow AC, but you do not allow DC. This is an important ability of capacitor because of the gap in it, because of the insulator in between the two plates, as I discussed in the beginning, the construction. It does not allow DC through it when it is fully charged. So coupling is one of the important uses. So these are some of the uses. The maximum uses so far they have asked in one question are 3, and they do not ask you to go in a lot of detail. They just want you to know just want to assess how much you know about their uses. A reasonable understanding of the uses will be enough. And now the first of its uses has a lot of questions, and at least one question which I have also shared in the recent worksheet. I would like to discuss it. This is a circuit with a capacitor here, and we have a two-way switch here. This is a two-way switch. You can connect it either to this side of the circuit or to this. Suppose you have an 8-volt power supply connected to this side, that will charge the capacitor when you connect it here. But as soon as you disconnect this side, when it is fully charged, you connect it to this side. This capacitor, which is charged, will now discharge through this resistance R. So charging and discharging can take place on choice. If we connect it to this side, the capacitor will be fully charged and it will have 8 volt of potential difference across this available. And as soon as you switch this to this side of the circuit, the two-way switch, you complete this part of the circuit, this same positive charge will rush through this, the current will pass through this, and this capacitor will discharge, taking a certain amount of time that depends on this resistance. and the voltage across this will reduce from 8 volt to certain smaller value. Let's discuss how we'll calculate the energy that passes through it, the power that dissipates in this circuit, and the calculations related to this. In the worksheet that I have shared with you, they have told us that through this resistance, as the capacitor discharges through this after it is fully charged to 8 volt of potential difference, this is V T graph. How the voltage drops when you allow it to pass through this. It starts from 8. Let's say this is the initial value of 8 volt. This is 8. And this is how it decreases. Let's say this is the manner in which the voltage decreases across this capacitor when you allow it to discharge through this resistance R by connecting this switch to this side. This is how you have connected now. Suppose this is 2 here, this is 4 here, this is 6 here, and this is 8. So this is about 1.5 volt after a known interval of time. Suppose this is exactly 1 second. If I divide this into various intervals, this is 0.5 second and this is 1. So exactly 1 second after you have this voltage left across the capacitor. And during this time, suppose we know the energy delivered to resistance R is equal to 0.13 joules of energy. This is given in the question. We want to calculate the capacitance if in 1 second, in all this time when the voltage drops to 1.5 volt, we want to calculate the capacitance. So the formula that we must use here is the change in energy, that is delta E. That is actually the energy delivered to R. So delta E is 1/2 C V1 square minus V2 square. This is the same formula we learned earlier, that energy is 1/2 CV square. That means initially we use 8 here. If I know the capacitance, I will have the energy stored on the capacitor. 1 second later, I'll use 1.5 here, and I know the energy stored with that potential difference across it. So I can take the difference of the two. Some students make a mistake here. They take the difference of these two first and then they square it. Instead of squaring 8 first and then squaring 1.5, they take the difference first, like 8.8 minus 1.5, and then they square it. Of course, that is different, and the incorrect result comes from that. So 0.13 is equal to 1/2 C. This is 8 squared minus 1.5 squared. So by using your calculator, you can work it out, and this is approximately 4,200 microfarad of capacitance that you can work out by taking the square of this, 64 minus 2.25, so 61.75 probably, and then you have a result like this. So you can calculate capacitance from this. But what if they have given the capacitance already and they want you to calculate the energy delivered? to that capacitor. So you use capacitance here, you use the difference of squares of these two voltages, and you calculate this value of energy. This will be simply the energy delivered to the resistor when you allow the capacitor to discharge through it. So any quantity can be calculated. If, for example, they have not given you this graph, they have only told you that this is the initial voltage across this, it gets discharged through it, this is capacitance. What is the final voltage across this? So V1, if V1 is known and V2 is to be found, then again the same formula will be helpful. So 8 square minus V2 square is equal to the known capacitance. The known energy delivered will give us the final voltage that the capacitor will have across this if it gets discharged from a certain initial value and it loses its energy, it loses its charge, and this is the formula that we use in that case. So a very useful formula which can be used to calculate various quantities involved here. One more type of capacitor that we have to discuss is a spherical capacitor. Is a spherical capacitor. It's the same sphere that you have discussed in the last chapter. A solid conducting sphere which is charged to a certain value. It also has an electric field around this. It has a certain value of potential due to the charge given to it. So it is also acting as a capacitor because of its ability to store charge on its surface, its ability to create an electric field around it, to give a potential positive or negative due to the charge on it. So spherical capacitor is simply a spherical solid sphere which is given a charge on its surface. As we learned in the last chapter, this sphere has an important property, and that is when you give a certain charge on its surface, you spread it over the entire surface. Let's say it is the positive charge Q. The capital Q charge is the total charge that you have given on the surface of it. By connecting a battery to it or by any other technique, by bringing a charged object to this surface, you can transfer charge to it. So by any means you have given a certain charge to this surface. Now it is insulated from anything else. So this is an isolated sphere. It's not in contact with any other conducting surface. So this sphere has a certain value of potential on its surface, and that potential is given by the same formula. If I know it has a radius r, it is k q over r. This is the same formula that we learned in the last chapter, and this is because the sphere has an important property. All that charge behaves as if it is concentrated at the center here, and it is just like a point charge, and at a distance r from it, the value of V is k q over r, and at all other points at the same distance we have the same value of potential. So whether it is a point charge at the center of a surface which has no charge, or it is a conducting sphere with a charge spread on its surface, it's the same formula that we use to calculate the potential at this point from the center of that sphere. If I use this K in terms of epsilon, you remember K is equal to 1 over 4 pi epsilon naught. So this epsilon is permittivity of free space. If you remember, sometime you are required to write this expression in this in terms of epsilon. So this becomes Q over 4 pi epsilon naught times R. So this is V. If I use the definition of capacitance, capacitance is voltage to charge. Sorry, this is Q over V, charge to voltage. How much charge you store per unit potential difference. So if you replace this V with this Q over 4 pi epsilon naught for a spherical capacitance, for a spherical capacitor, the capacitance becomes Q over 4 pi epsilon naught R. So this all simplifies to 4 pi epsilon naught times R, because this Q gets cancelled with this. So we have a new formula for capacitance, that is 4 pi epsilon naught times R. And if I want to write this in terms of K, it simply is R over K, because this is 1 over 4 pi epsilon naught times that is equal to K. So 4 pi epsilon naught is 1 over K. So R over K is actually C, which is the capacitance for a spherical capacitor. You are required to derive this expression, and there are various questions in the exam. After you have derived this, they might ask you to calculate the capacitance for a certain solid sphere with this radius, and then you are required to calculate how much charge it stores. If this is the potential on the surface, this is the electric field of the at the surface. So you know that expression for V, you know the expression for electric field is KQ over R square. So sometimes they give you the value of electric field, sometimes the electric potential is given, and with the help of these values you can calculate the charge that you have given to the sphere. Now, the last part of this chapter, and that is series and parallel combinations of capacitors. Series and parallel combinations. Parallel combinations of capacitors. You will see various questions in the exam in which more than one capacitors are connected in the circuit, and sometimes they are connected in series like this, and sometimes they are connected in parallel. They may be connected in, and then they are connected all to a single cell, a single battery with a known power supply, with a known value. This is, however, a series combination, and this is also connected to a certain known battery. Of course, they have different characteristics, and we need to know how we calculate the total capacitance of the combination. When it is series combination, we need to know how we calculate the total charge, the total energy. So a few important points are to be discussed. Number one is, no matter what the capacitance is, if you connect the capacitors in series, all the capacitors will store exactly the same charge. And that is, if by connecting a voltage V like this, which means capacitors are connected in series on the same path, all of them will have the same charge stored on them. So if you have positive charge Q stored here, a negative charge Q will be induced here, then the same charge of positive sign will be induced here, the same negative, the same positive, the same negative. That means we have the same charge on all capacitors, same charge. Even if the capacitance of each capacitor is different. Now come to this point. If you have the capacitor C1, you have a capacitor C2, you have a capacitor C3, and you have a voltage V connected across these three capacitors, now the charge Q will be different, and larger Q will be stored if we have larger capacitance because V is same. So Q will depend on C now. So Q is equal to CV. So if I want to know how much charge is stored here, Q1 is C1V, Q2 is C2V, and Q3 is C3V. So all these charges will be different. However, the voltage across them will remain the same. So it is same V in all those situations. Number two, this is same charge Q. However, we have different voltage drops across them. This will have a value of voltage drop across this depending upon its own value of capacitance. This will have its own potential drop depending upon this value of capacitance. Of course, all these values of potential drops, V1, V2, V3, they will be equal to V, just like any other series circuit in which we connect components in this manner. So V will be equal to Q over C1. This is V1. So V2 is equal to Q over C2, and V3 is equal to Q over C3. So this is a very basic point about this. We'll in the next lecture we'll move on from this. I close it here. These are two basic facts about these combinations of capacitors. We'll derive expressions for calculating the total energy stored, the total capacitance stored in this these combinations. That will be in the next lecture on Wednesday, inshallah. Thank you.